Well, welcome everyone. My name is David Leach. I'm the co-chair of the Thermoplastics Technical Committee at SAMPE, and welcome to the webinar today. We'll get started here. So today we're very pleased to have two presenters covering simulation of thermoplastic composite forming. Sebastiaan Haanappel, who's Managing Director of AniForm Engineering in the Netherlands, and Sebastiaan Wijskamp, who is General Manager of the Thermoplastic Composites Research Center, also in the Netherlands. Just a few items before we actually kick off with the webinar, and some background on SAMPE and the Thermoplastics Technical Committee as well. Please, in the chat, if you could enter your name, the organization, your position or role, and geographic location. That's kind of helpful for everyone to share, and then we can see that in the chat. You can see who else is joining and what their involvement is. And a little bit of background on SAMPE's technical committees. So there are now 5 technical committees. Obviously, thermoplastics is one of them, but there are also ones on advanced manufacturing, on bonding and joining, materials for extreme environments, and sustainability. And you can find out more information and join any of these groups, or more than one if you wish, through the SAMPE 365. The link is down there, 365.sampe.org. And then if you go to the groups, then that will show you the full list of all the groups, including all of the technical committees. Just a few items on what the technical committees have been doing. Obviously, this webinar is one example. Another major item is the State of Technology Industry Report, which SAMPE published last year, the first edition. This was written by the technical committees, so each committee wrote a section on it, so the whole section on thermoplastic composites in there. The first edition came out last summer, and the technical committees are now working on updates to that, which will come out this summer. And it's a great opportunity to get involved. And certainly in our group in thermoplastics, we had quite a large number of people contributed to the input, and it really benefits from having a wide range of folks contributing and joining in and sharing their knowledge. That can be downloaded at no cost from the SAMPE online store, as you see there, nasampe.org. SAMPE, of course, has been around for many years in the area of advanced materials. And there are a lot of benefits of becoming a member if you're not a full member already. First of all, you receive free access to the SAMPE journal, which is available as hard copy and an online copy as well. The digital library, which includes all of the published papers over about the last 20 years from SAMPE conferences and CAMEX conferences. So you can access those and download them at no cost. SAMPE has a wide range of local chapters right across North America, Europe, Asia as well. So you can join and get involved with the local chapters. There are discounts, of course, for the conferences and other events, and a lot of networking opportunities. Certainly, from my personal experience, that's been a big benefit of being involved with and a member of SAMPE over the years, of being able to get together with other folks involved in advanced materials. So you can join SAMPE by going to the SAMPE website or contacting the membership manager, Kelly Chin, and the email address is at the top there. Coming up soon, we have the SAMPE conference in Long Beach. where we'll have around 4,000 attendees. There's the conference, of course, with over 200 presentations, more than 250 exhibitors. So it's a great opportunity to see everything that's going on in the industry and network with other folks, suppliers and organizations and so on. The conference is the 20th to the 23rd, with the exhibition a couple of days, the 21st and the 22nd. And it's at a great location at the Long Beach Conference Center, right on the harbor area there in Long Beach. So of course you can register for that through sampe.org. Just to mention the Thermoplastics Technical Committee. We have regular monthly virtual meetings, usually the middle of the month. This would be the normal time for our regular meeting. And aside from the webinars, which we've had over the last 3 months, we do quite a lot of other activities as well. As I mentioned, we have written our section of the State of Technology Industry report with a lot of input from the members. I think there were something like 30 individual people all contributed in one way or another to the thermoplastics section. We are developing a supplier database of thermoplastic composites materials and fabricators that's being organized by Susan Ruth and Mike Buck, and we'll be talking some more about that in our next meeting. We have a literature club run by Lena Ganbury from the University of Southern Mississippi. That is a monthly event, a quick half-hour review of a paper. And this can be, might be a paper that you've written yourself that you want to share with people, or it could also be a paper that you have seen in the literature and you think is very interesting and want to share with people. I know Lena's always looking for folks willing to share things they've seen. So you can contact her through the SAMPE Thermoplastics Committee group site, or you can also reach out to me directly. I know personally I'm always pretty busy, and it's you don't have a lot of time to be digging through the literature, and it's a great opportunity to sort of get caught up with some current literature. And it's just a half-hour a month kind of review and discussion of the paper. Also, I mentioned a lot of the SAMPE papers and proceedings are available online, but some of the ones going back further are only available in the hard copy form, and Susan Ruth has been going through some of those. There's a lot of literature that's still very relevant to thermoplastics going back quite some time in some of the more fundamental science, early welding work and fiber placement work and so on. And our next meeting will be May the 15th, 4 weeks from today. And again, you can find out more about the Thermoplastics Technical Committee at the SAMPE 365 site, and you can click on the link for the Thermoplastics Committee, which will take you to this web reference here. I also wanted to mention at SAMPE Long Beach, the Thermoplastics Committee has been quite involved in the activities there. So there is a specific track for thermoplastic materials and processes with 17 presentations. There'll also be some other relevant thermoplastic work in other sessions, like there is sessions on the NASA High Rate Composites Manufacturing Program, or HICAM program, which include thermoplastics as well. There will be a committee meeting or a meeting for all of the SAMPE technical committees on the Tuesday morning. And then in addition, the Thermoplastics Committee has organized and leading a panel on welded assembly and repair of thermoplastic composites. We're very excited about this. We're going to take it from the sort of fundamental polymer level with Eric Jankowski from Boise State University, with a lot of simulations of the bonding process, molecular bonding process, which is relevant not just for welding, but for all sorts of assembly processes where you may be consolidating or doing fiber placement. And then Michelle Van Toren, Technical Fellow at Collins Aerospace, will talk about the aspects of certification. Julieta Barreta Robles from the National Research Council of Canada will talk about repair of thermoplastic composites. And then Cindy Ashworth from the FAA will talk about kind of some of the FAA background, and particularly how you look at thermoset bonding versus thermoplastic kind of bonding and welding. So I think this is going to be a really great session. Each of the presenters will give a short presentation, and then we'll have discussion and questions as well. And that is on the Wednesday afternoon of SAMPE, Long Beach. Also coming up even before then, SAMPE is organizing a tech briefing, virtual tech briefing. It is an hour-long event on April 30th, so just under 2 weeks from now, 10 a.m. Pacific or 1 p.m. Eastern. And each of the technical committees will give a brief oversight of current technology in their area. So again, advanced manufacturing, bonding and joining, materials for extreme environments, sustainability, thermoplastics will each give a brief overview. So again, it's a great way to really see kind of the state of the technology in various different areas. And again, there is no charge for that, although you do need to register in advance for it. The link is there, but again, if you go to 365 at sampe.org events, you'll be able to find that. And also it's being promoted quite a lot on LinkedIn, so you'll also find the registration information there as well. So let's just come back to the events of today. So as we said, the webinar today is simulation of thermoplastic composite forming. I also need to remind everyone that this webinar is being recorded and will be made available at a later date. If you have questions for the presenters, then please put that in the Q&A. If you could put your information in the chat, again, kind of your name, organization, geographic location in the chat, the questions in the Q&A, please. We'll actually hold all the questions to the end of both presentations and go through them then. So with that, let me hand over to Sebastiaan Haanappel, Managing Director at AniForm Engineering.
Thank you, David, for the introduction. I will share my screen. So, hope that all works. All right. Yeah. Hello, everyone. I'm Sebastiaan Haanappel, Director at AniForm. Yeah, I started as the second owner of AniForm around 10 years ago. And yeah, it's today really an honor for me to present to such a large group the state of the art on composite forming simulation, which will be extended with a talk by Sebastiaan Wijskamp from the TPRC on a deep dive in related R&D work. So, well, AniForm, that's us. We are a Dutch-based simulation technology company headquartered in Enschede in the Netherlands, and we spun off from the University of Twente in 2008. We're specialized in composite forming predictions. And in this talk, we'll show you our leading edge composite forming simulation technology, such that you can get an impression of the state of the art prediction quality. There's always a continuous demand for superior prediction accuracy, and such R&D related needs are facilitated by the TPRC, where they especially work on improving and developing material modeling and characterization techniques. Just to make sure we're all on the same page, I would like to sketch the scope on what we talk about today. So we talk about forming of composite laminates into part shapes. Usually we consider a laminate, which is heated, then we form it, we consolidate it, and then we release the part and we have a nice part. Well, not always that nice. During the forming, there can be some defect development, like wrinkles, some poor consolidation spots, ply splitting, well, all kind of defects that can, well, knock down your structural performance of the part in the end. Also, in the release stage, there's usually some geometric deviation occurring, also known as warpage or spring back, which gives some problems when doing part assembly in larger structures. It gives us fitting issues. We work on that kind of simulations as well. It's in development. That's not part of the talk today. Today's focus is on forming defects. And yes, it may be clear that there are quite some manufacturing challenges. So what about these? Well, what we see is really for each new part geometry, the complex material behavior of these composites in their molten stage, it really limits just using predictiveness by using common sense. And we see a lot of designer questions like, well, I have a process strategy in mind, but will it actually work? Will I have wrinkling or fiber waviness, and where does it occur? What about this poor consolidation? Caused a lot by fiber bridging, when fibers span corners, for example. What about my temperature? What about cold spots and crystallization? When I form a part, I get new fiber directions. We get material reorientation. What will it do with the structural properties? A lot of questions. And well, in the traditional approach, we usually go through many design iterations to answer these questions. So usually we have a part design. You think of a process design to make it. You take the part in production, and usually we have some issues. So you can go back to the drawing table and rethink about the part design and rethink about the process design. And usually you go through this cycle quite a lot of times, and we call that trial and error. And the slightly modern approach would be to use a process simulation software to minimize this number of design iterations. And that's why we thought, hey, let's support that and let's develop a software, which we nowadays call AniForm Suite. So that's a software package, and it has all kind of modeling possibilities. I quickly go through it. You can model various forming process configurations, just the classical one, a punch and a die, and form it. But you can split up the tool as well and go for segmented tooling and see what happens with the forming of your laminate. There are also other variants like pressure-driven forming processes where we talk about double diaphragm forming or hot drape forming. You can model a material by using a material card. We have them from renowned material suppliers like Solvay, Victrex, Toray, Teijin, John Mansfield, Celanese, and DuPont, representing a fabric or a unidirectional thermoplastic composite. You can play with laminate variants. So like a regular laminate consists of a uniform stacking of plies, where you can process in the blank, for example, cuts and darts. But you can also include ply drops and model tailor blanks in this way. You can also model fiber steered or fiber placed blanks. And then you can play around with how you handle the laminate, because there are quite some methods and you can study them in the software. So you can, for example, use grippers and springs and connect them to the laminate and see what happens. You can also use another kind of support like pin supports. Well, that's all nice. And you can create your model and then do a simulation. and a simulation is then solved by our autonomous implicit solver, a finite element solver. And that gives us quite accurate results today. And that is amongst others possible because we model the relevant deformation mechanisms that develop during forming a laminate. What about these deformation mechanisms? Let me explain you a bit what we take into account here. So let's identify these deformation mechanisms. And I would like to use this example for that, the forming of a dome, a circular blank, a punch, and a die on top. And we form a cross-plied unidirectional laminate like this. And if you form it, yeah, it typically looks like this. And if we take a closer look, you can draw lines here in the 0 and 90 direction, and we see that the material gets pulled inwards. And we also see there, well, that is because there's no stretch in the fiber direction in those directions. We also see at that locations no in-plane deformations in those indicated spots. On the other hand, if we draw diagonal lines here, we see some extension or stretch, and that is due to some in-plane shear that is developing here. You can clearly see that in the corners that these squares are actually not squared anymore. So what we see here is that there's some fiber inextensibility, which we need to describe, and there's in-plane shear going on, governing this forming process of this dome. So these mechanisms for sure need to be considered in the model. Going a step further, this was a cross-ply laminate. Now let's focus on the forming of a quasi-isotropic laminate. That means there's 0, 90, 45, and minus 45 fiber directions in there. And if we form that dome, we get a different result. We see quite some buckling going on. These are, by the way, the fiber directions in that laminate. We see quite some local bending and buckling going on. And if we completely close the press, these buckled areas are pressed into large wrinkles. So there's quite some out-of-plane mechanisms going on, and that means we need to really describe this out-of-plane bending behavior. We need to describe the out-of-plane bending rigidity in the model. The last deformation mechanism is about slip. So you may remember the first result with the cross-ply layup we had. It looked like this, a nice dome without so much wrinkling. And we saw a lot of deformation at specific spots, shear deformation. Suppose we have the same cross-ply laminate, but we rotate it by 45 degrees, then we get a rotated deformation field, where at this point we have now no deformation, whereas we had deformation in the other, in the original rotation. So for a quasi-isotropic layup, actually both situations are present, but then superimposed. And that gave us this result, a lot of big wrinkles. So what can we say about this? Well, that plies with different orientations typically deform different. They have a rotated, in this case, rotated deformation pattern. But it means at certain spots the deformation is hindered due to frictional interaction between the plies that is occurring there. And therefore, we can say that we need to model the friction between the plies. Oops. Okay. So the characterized deformation mechanism, we are in-plane shear for fabrics for unidirectionals. We characterize bending for fabrics and UDs, and we characterize friction for fabrics and UDs. And we use the bias extension test for characterizing shear of fabrics. We use the torsion bar test for characterizing shear of unidirectionals. We characterize the bending behavior using a bending test in a rheometer, and we characterize the slip using a friction tester. And that is a program today offered by the TPRC. So we have that characterization generally available in those results. Let's going back to the simulation. We want to create a model, and the domain we simulate is represented by finite elements like displayed here, all these triangles. Then in this model we describe we just observed them, the observed and characterized mechanisms. And these are described by calibrated constitutive models serving as an input for these finite elements. And we use different finite element types for the different deformation mechanisms. So we use membrane elements to describe fiber tension and in-plane shear. We use discrete Kirchhoff triangles to describe the out-of-plane bending of plies, and we use contact elements to describe ply-ply friction, but also tool-ply friction naturally. And yeah, let's see what we can do with such a model. And therefore, I have a little case study. It's a demo part. It is relatively deep. It has concave and convex flanges. We manufacture it using a woven fabric 5 harness carbon fiber PPS matrix material. It's also known as the Torii CTEX TC1100. We consider a blank. It's a laminate having 4 plies, initially now stacked in a quasi-isotropic manner, so 45s on the outside, and in the center we have a 090 ply or 2 090 plies, and we consider a square shape of the blank. And you can model that then in AniForm pre-post and do a prediction. So about this simulation result with a quasi-isotropic layup, we have the blank, by the way, supported using tensioners, and then you typically get the result like you see here in the video. So a lot of things going on. Let's play it one more time. Here you see the shaping of the laminate into that part. And here we see the forming progression snapshots. And what we see is severe wrinkling. And we see it in reality too. But what can we do about it? Well, we have a simulation to explore things. So we can change the layup, for example, make the laminate, for example, a cross ply. So just changing the numbers and do a new prediction. And then the prediction looks like this. Quite different. One more time. So here are the snapshots of the forming of the laminate. And we can conclude when we compare this cross-ply layup with a quasi-isotropic layup that there's quite some improved formability. And that is mostly because there's less resistance against in-plane shearing. We don't need all that friction between a 090 and a 45 ply in this case because of the absence of it. And this shear is plotted in this image as well. We see a lot of in-plane shear in the corners. And that's what you really need to have good formability when forming this kind of deep part. There's one little issue. So this is the situation. Laminate tensions like this, and then this is the resulting deformation. there's a little wrinkle that runs into the part area over there. We can zoom in. And well, what can we do about that? Again, we have a simulation tool, so we can do anything we want. So one thing was just to change the blank handling configuration. And by that, I mean to change the orientation and position of the springs attached to the laminate. So instead of 4 springs pulling diagonally on the laminate, we now put 2 springs per corner and pull, yeah, or perpendicular or in line with the fiber direction. And then if you do a prediction, you minimize this wrinkle. It gets just arrested before it runs into the actual part area indicated by this black line. This is the part edge. So the wrinkle gets arrested. That's how we call that. So that's quite a nice optimization effort, I think. Of course, we can do some verifications. We're a member of the TPRC, so we have access to the press over there. So we did a lot of trials in the past, and well, this was the situation, like you remembered, if you remember. So tensioning like this and tensioning like this. And we did that in practice as well. And if we zoom in on the part, if you look carefully, you see that the fiber directions here take a quite a different direction. The wrinkle is not that obvious, but from this continuity here, you can actually conclude there was a big wrinkle in there, but now masked away a bit by the huge pressure that was exerted on this part. And similarly, we tested this configuration, and you see not the presence of such a wrinkle, and you see nicely, yeah, nice uniform shearing of the material in that corner. Yeah, that's all nice. But yeah, what about predicting the smaller defects, smaller wrinkles? For that, I would like to talk about this example where we form a aerospace rib. With this layup, quite a special layup. We have fabric layers on the outside for this case. 5 harness carbon fabric with a low melting peak resin. And then unidirectional plies on the inside. This is how the forming configuration looks like. Blank shape was already optimized, and it is now connected to springs or tensioners. And then we can do a prediction. And it looks like this roughly. Well, not so much going on, I think. And when we compare with a real part in practice, then we can see that there was actually quite some in-plane wrinkling going on, especially in this curved flange. But if you look in the simulation, that is not so obvious at the first glance. So it's not so clearly visible, these kind of defects, the smaller defects we see in practice. Among other things, that is also simply because the finite elements are larger than the defect size, so things become a bit more complicated when it's about result interpretation. We can think about indirect wrinkle indication, for example, by looking at underlying results like the in-plane shear strains. And that picture is shown here. And we see at some spots here, these 2 spots, we see quite some irregular patterns of the in-plane shear. And we can also have a look at another result. We can have a look at the fiber stresses and then especially focus on fiber stress compression. Then we get this plot. So everything that's blue, green, actually everything that's not red is compression. And yeah, these 2 results actually can be used to indicate such smaller defects. That's quite indirect. You can make that task of analyzing a bit easier by using a wrinkle indicator. That is experimental yet, can be used, but it gives you some kind of wrinkling sensitivity. And under the hood, it looks at the results I just showed you. So you get a big orange area where the wrinkle sensitivity is between small and medium, and the red spots say, well, there's quite a big chance you will have a wrinkle there. So I would say, yeah, the issued area is quite well indicated. However, if you don't have the real parts, it's quite hard to be very conclusive about this kind of defect development when it's on this scale. And we also see that the industry demands a more precise and definitive defect detection. But to start doing that, we also need to look and dedicate research to refinements in material characterization techniques and the material models. To summarize, the current forming simulation technology, the state of the art, I would say it enables quite user-friendly modeling of the process in quite some detail. The predictions are reasonably accurate. Simulations are being used increasingly in industry over the last 10 years. And we already see that a lot. It makes the design process way more efficient already. But again, there's a continuous demand for superior prediction quality. And therefore, our developments require a refined material characterization techniques, refined material models as well. And such core R&D things are also facilitated by TPRC's research projects. So that brings me to the next speaker, Sebastiaan Wijskamp from the TPRC, who will do a deep dive into this R&D related work. Sebastiaan, may I give the ball to you?
Yes, thank you, Sebastiaan.
Yeah, and this is David. If I can just jump in for a moment as well, please remember, put questions in the Q&A, and we'll deal with all of the questions at the end of the presentations. Thanks. Back to Sebastiaan Wijskamp.
Okay, thank you, David. Thank you, Sebastiaan. So just a few words on the TPRC. So we are a scientifically independent research center created in 2009. So this year we celebrate our 15th anniversary. Hurrah! We were created to advance thermoplastic composite technologies. What we learn, we try to publish as much as possible, and the majority of our work is done by PhD students. So most of our work ends up in journal articles and PhD thesis. So dissemination is a big part of our work. And we also serve as a networking community. Specialists come together 2 times per year in Enschede to discuss our roadmap research. You see our partners here, mainly aerospace oriented, and I have highlighted AniForm, who has been a partner with us over 10 years already, and we've collaborated on many projects. Okay, I'm going to talk about our latest developments in the material characterization for forming simulations, and just showing a little piece of the iceberg, tip of the iceberg. As Sebastiaan mentioned, that wrinkles are a major challenge in stem forming, especially with unidirectional tapes. There's small wrinkles, waviness, marshalling, and there are some indicators that will point them, if you know as a user how to interpret these results. The large wrinkles or folds, larger than the element size, are quite obvious in the AniForm software. We really would like to understand and model these small wrinkles, both in and out of the plane. There's also other challenges, fiber matrix redistribution, voids, dry spots, maybe delamination, shape distortion, spring and warpage, apply splitting. We will not discuss these today. Today it's more about our characterization works. So we have our materials, can be unidirectionals, fabrics. We're currently also looking into other types of materials, so discontinuous fiber reinforced laminates, for example. Well, Sebastiaan highlighted already the deformation mechanisms that we have isolated, the characterization measurements, the subsequent material modeling, which is then used in our finite element simulations. Today, I'm going to look into in-plane shear characterization and ply-ply friction characterization and modeling, and also a new ply-ply friction apparatus that we have developed in the last 2 years. So let's have a look at ply-ply friction. So it's the resistance between stacked plies against movement. We need it because without slippage, less friction is better, because then layers can move with respect to each other. It will allow us to form V-shapes, for example, in the top picture, and also laminates with different orientations to move with respect to each other. In the past, we have developed a friction tester where we really try to manage the pressure distribution, temperature profile, measure the forces required to pull one layer out of between two other layers, or between metal substrates. So we can also measure the tool ply friction with this device. Well, if you look at the bottom of this slide, you see a small reference, and in the reference we also see Haanappel, and Sebastiaan was in fact the first PhD student to graduate with the TPRC. Typical friction response is that the shear stress grows, reaches a peak, and then drops down to a certain plateau value. So we recognize a peak and a long time shear stress. In the models, material models, we often use the long-term shear stress. It's more easy to model. Or we pick the peak stress. So AniForm offers both options. Most of the time, the long shear stress is considered here. Well, let's have a look at this single ply pull-out test, where we vary the rate or the speed with which we pull the layer from between the others. So in our curve, we see with increasing speed that our peak grows and we reach a certain plateau of the long-term shear stress. The gray line here depicts the average with arrow bars of the same measurement conditions on various samples. So you see that the error in that sense, the deviation is smaller than the difference between the averages. So that's good. And if you take all the peaks and all the long shear stress, you plot them on a log-log scale, you can create a so-called flow curve. And one of our researchers, Wijskamp, has been able to model this flow curve, both for the peaks and for the long-term shear stress. And here you see that until a certain point, the peak and the long-term shear stress, they coincide. That means that there is no peak. And we see that, for example, at the lower rate here. At a certain point, the long-term shear stress does not grow with the rate, and it reaches some kind of plateau. Well, Brens has been able to model that. So assuming viscous flow between two subsequent layers, where your shear rate is dominated by the distance between the two sliding surfaces, the plies here, and the velocity. It's non-linear viscous, so that means that we need a viscosity. We can measure that using rheometers. We also need a description of the interface, the interlayer between two plies. And well, here we already put dashed lines, so it now looks quite obvious to recognize the individual plies, but without these it's quite difficult. But it's there, and this interlayer can be described either from micrographs or simulating them with mathematically. So we have a description of this interlayer. We have our viscosity, so we are able to describe the stress growth and the stress. We can describe the peak of the shear stress. Thing is, here, after the stress peak, there's a decrease to this long-term shear stress. But that can only happen when there is slip happening at the walls. So the peak stress is modeled with a no slip, so a stick condition. Here there must be a certain slip, and for this, when the shear stress is higher than a certain critical stress, slip occurs, then we have the drop. And this critical stress, we take the value of the plateau that we saw earlier. We see different heights in our interlayer. So here, really, the shortest distance, so the shortest height, dominates the occurrence of the shear stress. And when all the points in the cross section have reached the critical shear stress, then there is full slip, and we reach our long-term shear stress plateau. So as we are looking at small wrinkles, that means also small displacements, small slips, then we would also like to be able to describe the full stress strain or displacement curve. So we need a transient shear flow model. Our researcher chose to describe the bulk behavior of the polymer with a White-Metzner viscoelastic fluid and look at slip at the polymer matrix fiber interface. And we hypothesized that this is really the mechanism that will lead to an increasing slip velocity, leading to with which you can actually describe the decrease of the shear stress from starting at the shear at the peak stress. Then you get into polymer mechanics. It's about the disentanglement of polymer chains at the wall. You can reach an equilibrium. Disentangled polymers can also go back to the wall. There can be reorientation and relaxation. So you can do a state rate analysis, make a model where polymer state can go back and forth between different states. In the end, this ends up in a set of differential equations which you can solve. That goes too far for this presentation and definitely for my brain. But our researcher was able to solve this problem, and we actually got to a very good description of the stress displacement curve as measured. So here, one model we could fit to varying rates describing the full curve for different materials. So we took carbon peak and carbon low melting peak. So very happy with that result. Now we talk about friction testing. Here you see the original friction tester. It, in fact, is two pressure bellows that push heated platens against the ply-ply configuration, and you place this into a tensile tester and then pull the ply from the two plies, and it's all displacement controlled with our universal tensile testing machine. It's tedious work, need some operator skill here, and with, say, an outlook on further and more characterization work and growing importance of good, robust measurements, we decided to develop a new friction tester. It's we have considered upgrading the previous one, so it would be we would be able to use it in a universal tensile testing machine. In the end, we decided to go for a freestanding unit. So here's a clamping and heating device. Here's a cylinder that can pull the ply from the two plies here. It's all the pressure is very well controlled here, because if you have any misalignment between your platens, then you will generate pressure peaks that will mess up your measurement. So a lot of attention has gone to that. It's a very stiff, non-compliant setup. We can pull with kilonewton at least without any movement of the machine itself. We can do this by force and displacement control, so that adds more possibilities for research into stress relaxation, for example, and creep type of measurements. We can vary the rate, so accelerate or do steps, and it's very robust and operator friendly. And we're currently benchmarking this machine against our old friction tester and also friction testing activities that are going on at the KU Leuven, University of Warwick, Johannes Kepler University in Linz, and Fraunhofer UCT. And we've chosen here Torre, low melting carbon PEEK, and we run a set of experiments at varying speeds, pressure, and temperatures. So that was friction testing, as to describe one of the mechanisms. The other was in-plane shear. Well, if you look at woven fabrics, then quite a lot of people have used the picture frame, generate in-plane shear with a relatively simple analysis, or the bias extension test, which in terms of executing the experiment is a lot easier, but you have to put more effort into the analysis. We have tried both the picture frame and bias extension test in the past with unidirectional tapes. Would this work? You get enormous localization here if you try to test unidirectional materials with a picture frame. If there's a little bit of misalignment, you create enormous fiber stresses, and there's then delamination, localization, you name it. The same goes for the bias extension test at the time. So we chose then to look at in-plane shear through torsion of a thick beam. So we create thick laminates, 10 millimeters thick or more. We cut bars, put them in the rotational rheometer, and can control very well the temperature and the angular velocity in the rheometer. And with some analysis, you can get in-plane shear behavior from that specific setup. Big drawback of this test is the preparation time and the amount of material that you need. So Dennis Brands, one of our researchers, thought, I'm going to give it another try with the bias extension test. We also learned that we were able, with certain thermal treatment, to limit the deconsolidation or even prevent the deconsolidation of unidirectional laminates. So drying for a bit longer time at higher temperature really helps to get the coherence of the material and no delamination. Machined a dot bone, so from the laminates, for a good introduction of the force into the laminate. Using a template to make this crosshatch pattern plus dots, so that you can recognize 4 dots here. Those are used by the extensometer to measure strains in 2 directions, and the crosshatch pattern is to analyze the complete deformation field. And we perform these tests in a universal tensile testing machine at temperatures above the melting temperature, or after cooling down from the melting temperature to a temperature above the recrystallization temperature. So as said, the shear angle can be measured by the video extensometer. Post-mortem analysis could be done on using this crosshatch and the video picture image analysis. And zooming in some cases, you could see also the onset of localization, but only at very, very high deformations. Just to recap, doing a lot of experiments, we could say that the measurement of 2 strains with the video extensometer works really well. We are in a rather uniform strain state in the middle of the specimen. It's the same methodology as a woven fabric. And we can use this for large deformation and very high rates. These are the typical curves that you see. Up to a certain displacement or shear angle, they coincide with a pin jointed net. That would be the most easy description of the bias extension test. So we continue using this bias extension test and are currently also benchmarking it against the torsion bar. Most importantly, a researcher is now creating the models, finalizing the models with which a material card in the end for AniForm simulations can be measured. Now, another thing that we, a small tool or method that we developed over the last years in terms of forming experiments is this hemisphere or dome that Sebastiaan also showed in his presentation. He demonstrated all the wrinkles that occur, for example, with quasi-isotropic laminates if you try to mold the full dome. We found out that if you stamp form strips with various widths, that you can see at which width for a certain layup the first wrinkles occur. And if you then simulate all these measurements, you can really validate your simulations. You can also start calibrating your wrinkling indicators here. For that, you need a good idea of the deformations that occur. So again, Dennis here spent a lot of time in devising a way to put a lot of small dots, 1 millimeter with a 3 millimeter grid, on a laminate, and perform an analysis with photomodeler, so photogrammetry, before and after the stamp forming. And if you, this is a turntable with reference mark here. You have a camera on a fixed point, you rotate this table, and you get 16 pictures, and from that you can get the coordinates of the dots in the 3-dimensional space. Now, we've done this for quite a lot of layups here. Different widths, 2 materials, so that means 48 parts to be analyzed, looking at wrinkling and in-plane deformations. Again, here materials chosen were Toray TC1225 and Solvay or Science Co APC. In terms of achievements, yeah, we are now able to very accurately measure our deformations. All the data of this set has been published. So that's data in brief, I believe. It's available, so you can have a look at all the pictures and analysis. And currently, we're comparing these experiments with AniForm simulations. Now, just to go back here, you see the analyzed deformation on the part. We take an average here. You see the white spots, those are dots that are missing because they are folded and not visible anymore. So this is what a typical deformation analysis looks like. And all of these experiments are being virtually repeated, so simulated with AniForm and incorporating a new description for the bias extension, for friction. You can tune other parameters as well, such as bending, adhesion, typical things that are available in AniForm. Just a small glimpse. Here we are comparing simulation to the experiment, and we see very good correlation there. Yeah, we can use the AniForm plugin, so a little environment where we can incorporate our own developed material models and test them before, if the interest is there from AniForm, they will implement it in a robust and industrial way. Dennis and Rens are finalizing their PhD. So we kind of covered the friction and the bias extension. And next step is the start of a PhD project on more advanced description of the bending phenomenon. And we'll start this year. With that, I would like to conclude both of our presentations with saying that the forming of thermoplastic composites is state of the art. Parts with moderate complexity already fly and are in cars today. Just doing process implementation, it will cost you money. It will cost you a lot of tools. So we really believe that process simulation tools will increase the speed of the market implementation. With a growing and continuous demand for better prediction accuracy, higher fidelity, we need more advanced material modeling. So we continue working on that. And our material characterization methods and our validation tools are evolving, and we think successfully for forming. And with that, I would like to acknowledge there are two researchers that performed all the work. So Dennis and Rens are defending their thesis this year. They've published already a lot in different magazines and popular and scientific. And thesis will come out. Keep an eye on them. My thanks to them.
All right, thanks very much, Sebastiaan and Sebastiaan. I realize we are kind of at the original assigned time, but we can carry on a little bit and at least answer some of the questions that came in. I guess, first of all, for Sebastiaan Haanappel, one question is, what solver is used, and is this in-house or otherwise created?
Yeah, thank you for that question. We developed our own solver. So,
right,
the AniForm solver.
Yeah, so it's proprietary to AniForm.
Correct.
Okay, all right,
Yes.
thanks. One question, I guess, from a couple of questions related to the characterization of the materials for AniForm. One of the tests is the bending, and one question is, why is it not possible to get the bending properties from the in-plane properties and the geometry?
Yeah, I see. So I think for unidirectional material, there should be a way to do that. Though I think you need to rely there on transverse isotropy. But I believe here what's meant that when you shear a unidirectional ply, it can also shear in plane and through the thickness. It's principally the same shear mechanism, but in practice that deviates a bit due to a deviation from the usually assumed transverse isotropy. But with some correction, I think that is possible for unidirectional. So that could be very well good follow up to match or try to bring together the two different deformation or two different characterization tests. For fabrics, however, that would not be the case. There you still, for sure, always need to describe these mechanisms separately. But yeah, it's a good point.
And maybe it's a related question to characterization. How long does it take to characterize a new material?
From say reception of material to delivery of the fit, so the card, 2 months.
All right. Some questions for Sebastiaan Wijskamp from your presentation as well. So the image on the friction slide shows the fibers all running in the same direction. Do you run tests for cross-ply friction, or would you expect those to be the same?
Yeah, good question. So so far we have done all 0-0 experiments, because the current friction tester with UDs does not allow us to do cross-ply. With the new generation friction tester, we can do that, and we will. So it's on the roadmap. But definitely this interface description will change in that respect. Yeah.
All right, another one for Sebastiaan Wijskamp. How does the critical shear stress change with the fiber volume fraction? And what was the fiber volume fraction in the experiments you showed?
Yeah, so the fiber volume fraction was about 60%, 59. Critical shear stress. So the fiber volume fraction dominates mainly the interlayer behavior. So with higher fiber volume fraction, then the amount of matrix between the layers will reduce. So it will have an effect on the peak stress. I think also the critical shear stress is affected, but I forgot in which direction, so I can get back to you on that.
Right, and then a kind of related question: how many plies do you assemble for the shear tests?
8.
More questions on the shear characterization. So does the extended drying time, which was necessary to do the bias extension specimen, does that influence the mechanical properties of the material?
Nope.
All right.
No, we're above TG, but well below the melting temperature.
Yeah. And do you have any preliminary results for the comparison between the new test and the torsion bar test?
Yes, we do, but not in the public domain yet.
Okay.
It should be there in a couple of months.
All right. Okay.
Yeah.
The tool material interface, is there any kind of tribological, frictional or other effects that you need to consider?
Yeah, so normally we do full characterization of the tool ply friction as well. Tool material, tool surface, tool treatment with release agents all play a role, can play a role.
Another question: is it possible to apply fluid pressure instead of stamping in AniForm? I guess more hydrostatic type approach.
Yeah, I'm not really sure what is exactly meant. By default, yeah, a hydrostatic pressure cannot be applied because we use shell elements. However, we do have 3D elements which can be equipped with such bulk models. But I lack the context a bit, so I cannot actually answer.
Can AniForm analyze the effects of defects from the forming or export these for other analysis, such as in FEA? So if you identify a defect from the AniForm?
So we have interfaces to other software. They don't take into account the quantified defect itself. It does transfer new fiber directions and thickness, and optionally forming induced stress. But the defect itself, when do you quantify defects actually, that identification is not transferred, and you also need something to describe such a knockdown. But it can be done manually if you have a way to identify the critical region and then apply knockdown or something. All the results from AniForm can be exported and manually be interfaced to other software. So yeah.
All right, thanks. I know normally we're dealing with multi-ply laminates, but one question is, what about very thin thicknesses, such as just 2 plies? Can you look at that, okay?
Yeah, that's all possible. You can model any plies you like. So it is possible, yes. It's usually when you start an initial simulation, you want to quickly check whether you modeled everything right. The advice is even to just model a single ply laminate. Yeah, so that is possible, yes.
Right. Maybe one last one. I know we've got quite a few questions come in, but I want to be respectful of everyone's time. So AniForm makes predictions of the values for the stresses and strains and shear angles. Do you have a reference on the thresholds within the material cards as to when they occur, or do you have to validate with real parts? And get just a sort of relative sense from AniForm as to when the
right. Yeah. We have not yet established sets of thresholds which would ideally be related to one specific material. It's at the moment thresholds are general, and you can calibrate them yourself using your own experience and comparing with your own products. That's today how you can approach this. But it's on our roadmap indeed to get a more refined set of thresholds, really connected to one specific material. To achieve this, you indeed need to compare to actual results. So there are also developments to extend the current material characterization program by this discipline.
Right. Very quick one on the characterization for Sebastiaan Wijskamp. What temperature do you use for the rheological torsion test?
Yeah, so for all tests we use the same temperature range, temperatures, 360, 380, so say 20, 40, 60 degrees above melting temperature.
Right, so it's
be careful not to go too high, of course, then we would experience degradation. So between 340 and 385.
Right, so it would be kind of related to a typical process temperature for each polymer, kind of above the temperature.
Yeah.
Right. Maybe one last one. Is it possible in the modeling? I guess this is more Sebastiaan Haanappel. Is it possible to use a rubber die in the AniForm which deforms under pressure? So can you account for the tool kind of distortion as well?
Yeah. We received the question a lot, but unfortunately my answer is always, we cannot do that yet. You really need to have suitable 3D elements to describe the rubber deformation, and as rubber is incompressible material, it's really difficult to describe that numerically. We have not dedicated our efforts to that problem actually yet.
Okay, thanks. We're kind of 15 minutes over what we thought. I think very interesting presentation and lots of questions. There are a few questions unanswered, but we will try and capture those and have Sebastiaan answer those offline. Once again, just to remind everyone, this webinar has been recorded and will be available at a future date. We'll send the information out to everyone. when it is available. And so thank you one more time to Sebastiaan for a very interesting webinar. Thanks.
Thank you for hosting and thank you for your attendance all. Have a good day.
Good day.
Thanks.